All right, here's an example problem for learning objective 1 in magnetostatics. So this is finding the magnetic field due to current sources. And you might recognize this picture. It's one of the pictures that we looked at in class. I thought it would be a good way to practice these problems. So we have 4 current carrying wires at the squares of a square, at the corners of a square. And the direction of the current is shown, so the dots are current coming out of the page and the cross is the current going into the page. Each of them have a current of 3 amps. The sides of the square are 1/2 meter in length. We want to find the magnetic field at point P. So this time, instead of ranking them like you did in class, we're actually going to do the calculation. So I've labeled the different currents with a number and a color, so I'm going to try to make it more obvious by using color coding. So I'm going to do more drawing with the first one than I do with the other ones, just to kind of talk about how we figure this out or how we show the direction of the magnetic field. So keep in mind that the magnetic field makes circles around the current carrying wire, and we use the right-hand rule to figure out the direction the field goes on the circle. We put our thumb in the direction of the current, and the way that our fingers wrap around our hand is the way that the magnetic field wraps around the wire. So I drew that circle there just to show you. And so I imagine the circle getting bigger so that it just touches point P. And then my magnetic field direction at P is tangent to the circle. And so this would be the direction of B1. Now I'm going to do this with the other wires now. I'm going to move on to wire number 2. Again, I'm going to kind of imagine a circle. And now for this one, because the current goes into the page, the magnetic field will wrap around in a clockwise direction. And so keeping that in mind, my magnetic field at point P due to wire number 2 is going to be in this direction. Okay, so now I'm going to do the same thing for 3 and 4. Again, I'm imagining the circle tangent to point P, and then I want to draw my arrow at point P tangent to the circle. So B3 is actually in the same direction as B2. And then finally I'm going to do 4, and B4 is going to look like this. All right, so I've drawn all my magnetic fields. If you're looking at these arrows, because of the fact that all the magnetic fields have the same magnitude, and the reason for that is because my distance is always the same from point P to the wire, and all the wires carry the same amount of current. So the magnitude of all these fields is the same. I'm going to end up calling it B at some point, and it's equal to mu naught times the current over 2 pi r. If I do the calculation for r, I get that it's 0.354 meters. That's pretty easy. You can use the Pythagorean theorem to find the length of diagonal of the square and then take half of that. And if I look at the picture, I can see that from my picture, B1 and B4 cancel. And so B3 and B2 add up. So B3 and B2 are in the same direction, up and to the left, and B1 and B4 cancel out. Despite that fact, I'm going to kind of brute force this just to remind you how we would find the magnitude and direction of the net magnetic field or the total magnetic field. First of all, I want to just go up here, and this is find the magnitude of the total field by putting in my values. And I find the total magnetic field of each one of these is 0.19 Tesla. So that's B. All right, so in order to find the x component of the total x component, what I need to do is find the x component of each one of these individual vectors. Because it's a square, I did that on purpose. It makes it really easy. The angle that they are tilted at is always going to be 45 degrees relative to the x or the y-axis. So for my x components, I have b1 times the cosine of 45. It's in the positive x direction. b2 and b3 are in the negative direction, x direction, and so is b4. Because all the b's are the same, remember that, I could just make these two cancel out, and I'm going to get minus 2b cosine of 45. So I get minus 2 times the 0.169 times the cosine of 45, and that will give me a net magnetic field in the x direction of minus 0.239 Tesla. Now I'm going to do the y components. B1 has a positive y component, so does B2 and B3. B4 has a negative y component. Once again, I could cancel these two out because the B3 and B4 are the same in magnitude, and my total By is 2b sine of 45. Since my b is the same and sine and cosine of 45 are the same, I know that this is going to be 0.239 Teslas for the By. So now I can find the total magnitude is the square root of bx squared plus by squared. So it's going to be the square root of 2 times 0.239 squared, because each of the components are the same. That's kind of easy for this one. So my total magnitude is 0.338 Tesla. So that's my magnitude. My direction, I'm just going to do it as a way to remind you of our method. And if I do that on my calculator, my angle will be minus 45. It's because of the x component. I know that my net magnetic field is in the second quadrant, so I could say it's 45 degrees measured clockwise from the negative x-axis, or it would be 135 measured counterclockwise from the positive x-axis. So remember, in order to completely describe my magnetic field, I have to give both the magnitude and the direction of the field. So this is how we might do a typical problem for learning objective 1.